Hi, all. Chelsea here. First things first, I just want to caveat that I'm quite tired. I've been burning the midnight oil, so don't expect this to be too serious of an intense class or anything like that. I just want to get that out of the way that I'm pretty tired. I've been burning the midnight oil for a bit. So about me, I'm just going to say what I do because I know that I have a reputation that precedes me elsewhere outside of what I actually do on a daily basis. But what I actually do is I have a history of doing software development. I've been doing software development since I was around 13, 14 years old. I was in my first startup company at the age of 17. And I've been working with compiled programming languages such as C, Visual C, Visual C++, Objective-C later on with Apple products, and more recently Rust. I do a lot of systems administration work, your AWS, your bare metal systems, edge computing. I work with a lot of containerization, mostly Docker containers, virtual machines and whatnot. I'm also primarily I do security consulting, so I do mostly blue force analysis. I look at what a client is actually doing and what their potential threat models are, and then get it prepared for get an analysis done, prepared for pen testing. I don't actually do pen testing anymore, at least. So another thing that I focus on is with hardware encryption modules, which is where that particular portion of this is where I've had an interest, and I've been looking more and more at microcontrollers, and particularly Rust and microcontrollers. If you want to know my Twitter handle, that's my big Twitter handle there. We will return to that. So why microcontrollers? Why would you want to put Rust on a microcontroller? Well, it boils down to the fact that most microcontrollers that we have today have enormous amounts of security vulnerabilities. There have been dozens of highly sophisticated, documented bare metal industrial control systems attacks. First documented in 2009, could be older than that. We're not sure. But in 2018, one major security consultancy firm, Kaspersky, I think is who it was, identified over 60 vulnerabilities in industrial Internet of Things systems. So your industrial controls for oil refineries, for manufacturing facilities, for power grids and whatnot, are running on a lot of these things are running continuously for years on end with very little updates in terms of firmware, with very little awareness from the security, from like a security perspective, because you expect, oh yes, this machine, it's working, it's running. I don't seem to have any problems with this. Why why would we want to look into this? And this has been the cause of a number of very sophisticated attacks that manage to hop from device to device, usually on a targeted system, especially if you're a large facility like a factory or some kind of refinery or mill or something like that. So. Centrifuges for nuclear facilities have been targeted before, or at least rumored to have been targeted before. So these kinds of things exploit the fact that nobody's changing these things. Nobody's really looking at the software that's in them, and they're not built with security in mind. So most modern microcontroller-based systems use the same components by a few manufacturers, so they sort of are not brand names unless you are really in the microcontroller space, but your Espressifs, your can't think off the top of my head all of a sudden. But you know, like your Texas Instruments, your whole gambit of all these different like 1980s, 1990s microcontrollers that pretty much do very simple things. You know, they detect whether there's an input and an output from a switch and flip it. They measure things. They take sensor data and they interpret that. So very simple kernels, very simple instruction sets, and they work. So you don't update them, you don't look at them, you don't have to worry about them. Well, more recently, now we've entered into the era of RISC-V, which is one of the reasons why I got so interested into the new sets of microcontrollers. Now, RISC-V is an open source architecture. It's 32-bit. It's highly efficient. It's very similar to what is in most mobile phones. You know, if you think of your Intel system and your AMD system running x86, it's a CISC system, so it's got a very complex instruction set, whereas like ARM, you know, has a much simpler one. RISC is also ARM, but it has it's not ARM, but it's very similar to ARM, but it has the advantage of being open sourced, which allows for manufacturers of microcontrollers in particular with the 32-bit instruction set to be able to manufacture these things much more cheaply than than having to go to ARM and get a contract to use their patented designs and things. So you're able to. So there's a lot more flexibility in the IP, which allows smaller manufacturers to be able to churn out very highly efficient, microcontrollers. For industrial applications, more specific things. In the cryptocurrency space, you'll often see them use an ASICs, for instance, in order to be able to just crunch a particular set of algorithms in order to more efficiently mine for cryptocurrency or do proof of stake in a blockchain system. This particular ISA was devised by I believe two PhDs out of Berkeley in 2011. They wanted to focus on making an instruction set that was very educationally friendly, but in doing that, in creating an open source instruction set, they without really intending on it, they basically enabled larger companies to come along later and look at the open source standard here and say, oh, okay, we can't compete with AMD and we can't compete with ARM and we can't compete with these gigantic IP companies, but we can use this. We can invest in development of chips that use this instruction set, this very simple instruction set and very efficient instruction set to be able to do these things. And so, and now more recently, Sci-Fi has released 64-bit CPUs as opposed to microcontrollers like the Unleashed and the Unmatched, but they're more development boards, and there's more interesting things coming along. But the particular chip that we're going to look at is the ESP32C3. The ESP32C3 is a RISC-V 32-bit microcontroller. It is brand new. It's only been around, I think, for about a year and a half. It's been in the open market. It costs about $1 for a single chip. So it's an extremely cheap, it's an extremely efficient, and it's extremely low power microcontroller that can be used for so many different things in so many different systems. And chances are, if you own a modern graphics card, that was made in the last year and a half, and you were lucky enough to shank out, not have to shank out $1,500 for it from a scalper, then you're probably going to have some of these microcontrollers in systems in your desktop and in your desktop computer today. The advantages to the ESP32C3 are that it's highly cost effective. It's roughly $1. Even with the chip shortage, it's maintained a pretty low cost and pretty high availability. It's very energy efficient. It lasts for, it can last in very harsh environments for, months to years on end. It's low. It has low. This one is Wi-Fi enabled, which is one of its advantages. It uses a 2.4 gigahertz standard Wi-Fi module built into the chip itself. It has low power Bluetooth 5, low energy connectivity, specifically with the ESP32C3. You have the advantage of it having some additional modules that allow you to have more cryptographic hardware acceleration, which is more my area and why I have an interest in these things. So your standard RSAs, your standard AES encryption, your block ciphers and things, they can be done more efficiently, and they can be offloaded from some other chip or process on the board, and just be able to do more secure things. So if you want to do encrypted radio communications, you want to encrypt. Say you want to make a say you want to make a small Wi-Fi device, or you want Wi-Fi connectivity for an industrial microcontroller in an IoT environment. Then instead of having to need a very large and very complex CPU that uses up a lot of energy, you can just use a simple microcontroller that has some of these capabilities. Now then, a particularly useful, and as you can see, there's also peripherals and sensors and things, and it's pretty good. I just downloaded that real fast, and it's got pretty much all of the different things, although I myself haven't even looked at all of the capabilities that are available for the ESP32C3, because my focus area is on the encryption modules. Now then, this particular board, a board that I brought with me, in fact, it's not. This is the breadboard itself, and then this is the actual board. This is the actual dev board itself. This is a custom design, very recently made dev board in an Arduino form factor. So it's not an official Arduino. It has additional components that are available for it that would not be on an Arduino Uno or a clone of that. So there's a couple extra modules and things for development. It supports USB-C, so it has a USB-C on there, and as opposed to like the micro USB that you would typically see on one of these things. And it's got the standard I2C and serial outputs, the JTAG pinouts. So it's got some RAM. It's got the integrated Wi-Fi and Bluetooth abilities, which the chip itself is on there. As you can see, right here, that tiny little thing is the actual chip itself. So that, let me see if I can get a cursor there. I didn't bring a thing. I can't see anything. But it's extremely tiny. It's about like a quarter the size of my pinky nail. It's an extremely small but very powerful little chip. And here's an example of a pinout for this thing. But we've talked about this device. So why are we here? Well, it turns out you can put Rust on this thing, and why would you want to put Rust on this thing? Well, the reason why is because Rust is one of the advantages to Rust is, from a security perspective, is the fact that it's memory safe. The fact that it's a much more secure and capable compiled and flashable like binary that you can put onto a chip. And it manages everything, and you don't have overflows, and you don't have all of the you don't have things left over in the memory and whatnot. And it's so you can use this. You can use Rust to be able to run very efficient and very secure code on this type of on these newer types of microcontrollers. So we're going to one of the things that we're going to try to look at right now is we're going to try to make this happen. So I just need to figure out how to get my virtual machine over here to over there. Maybe there's a means or a method that I need to look at. Is there an AV person?
Sorry, what?
I need like an AV person because I need to be able to get my virtual machine screen over there.
Mirror the display, is that?
Yeah, it's. I just need this there. So this is a virtual machine screen.
Yeah.
Why don't we just make it a window? Exit full screen.
Oh, now that thing died. Okay.
Okay.
Oh, no, it's back. Oh, yeah, there it is. There it is.
And then I make it full screen again. Maybe?
Yeah. Yeah, there it is. Do
I can't see the buttons.
you want to? Okay.
Oh, there, it worked. But now I can't see it here. That's all right.
We did it.
Yeah, we. All right, so here I've taken all of the different scripts and things to look at for how to set up a Rust environment that works for RISC-V and specifically to be able to build for a RISC-V 32-bit chip. Now then, the code there's a lot of these things are on GitHub. Like they're kind of, the explanations aren't the best in the world because there's not a lot of documentation on this stuff because it's so hot. It's some of the stuff is only 9 months old. Some of the stuff is like in subreddits of like on threads that have like 4 people on it. So but I've managed to at least sort of condense all of the different things that are needed in order to be able to flash from at least my desktop PC. I haven't been able to do it on an M1 yet, on the M1 MacBook yet. But to be able to flash onto the ESP32C3. So the first thing that we have is we pull up Rust. We pull up the standard Rust up. Pretty standard stuff if you've ever installed Rust on your box before. You set up a cargo environment. Now then, this is where things start to deviate. You're actually going to add a different environment. You also have these dependencies up here that you're going to need for this process. So I have those in there. And this is a Ubuntu environment that I have. This is an Ubuntu virtual machine that I'm running this in. So you have a target here, which is RISC-V 32i, unknown none ELF. That's going to be specifically for the RISC-V target. And the 32-bit target at that, as opposed to the 64-bit. The install prerequisites for the ESP2 devices, you're going to have a cargo install for LD proxy, ESP flash, and ESP monitor. These are tools that are already in the cargo, which are already in the cargo or the cargo environments that are specifically made to be able to work with ESP aspirative devices. Now then, your default environment is going to switch actually from either stable or nightly, and you're going to have a custom environment for this kind of thing. So the custom environment is going to be done with ESP. So it is going to be its custom environment, and then there's this thing called ESP IDF, which get clone recursive all this stuff here. That's how you pull it up. And basically ESP IDF is, and I can actually read the description on the thing here. ESP IDF is, I'm going to pull up the GitHub repository. ESP IDF is the development framework for the ESP32 system, and it's actually the development environment, the stack, if you will, for development on this chip is already pre-done. It's in the GitHub repository. It's already pre-made, and you can install it. And Rust will integrate this into Rust will integrate and build on top of the Espressif custom environment. And then here I was trying to set up for an example. So in here I was just taking the Rust ESP32 example main, which is its standard Rust environment, and trying to build like a hello world type tool. So we can actually go ahead and pull up. I think that I can actually run this, if I'm not mistaken. I can actually run this up to a certain point, and it will run pre-done. I just can't remember which one because I can't see. Go back to home, stop script. There we go. And then it should just fetch all the repositories. It'll run through. Here we're just gonna do a custom installation. Standard triple for this ARM because I'm running on an M1. Default tool chain, we'll just put nightly just because it's going to change anyway whenever it gets to the part where it switches over to ESP. We'll go with a default install. Modify path variable, we'll say yes. Proceed with installation. Default, yes. And so then I've already, this is already basically installed, so it's going to download some stuff, and it's going to download some of the prerequisite crates in order to run this install. But I've been able to test it up to a certain point. I have not been able to, which was the unfortunate part because I only got 70% done. I have not been able to actually, from the M1 MacBook, flash from a virtual machine onto the device here. But we have a little bit of time, so we're gonna play around and try to see if we can find out.
Yeah.
Yep.
Quick question. So
Yes.
I've used an ESP8266 before.
Yes.
I'm very new to microcontrollers. Like, is it common for them to keep the same name of the ESP32 and ESP8266, but like completely change the instruction set?
So the older ESP series, the 4-digit series, was replaced with the ESP32. Now the reason why they did that, I don't know why there's the nomenclature change per se, but the newer chips, I would say, like from I think 2014 is whenever they started, or maybe even earlier than that is whenever they started to switch over. And so now the nomenclature for some of these chips, because the S series are the old architecture, so they are just standard ARM. Now that you can run Rust on these things, so it doesn't have to be RISC-V, but the RISC-V, when you're developing on the RISC-V set, you are going to encounter less problems because it's native to the Rust environment that comes with Espressif. So if you want to do if you want to flash software onto an older ESP nomenclature chip, like the S1 or the S2 or the S3, you're probably going to encounter a lot more problems. There's a lot more hoops to get through to run a Rust application on, to run or to flash a Rust binary on there. Any more questions? Because I'm yes.
Is there any kind of operating system on there, or you're just running completely bare metal on the
So you can run simple kernels on there. There is. I mean, it's still an ELF. So it's going to be very similar to an extremely small operating. Yes.
What's ELF stand for?
Oh, ELF. I don't know. Oh yeah, there we go. That's the word.
I heard format. Executable looking format. Okay.
Yeah, it's basically how it's. I mean, I just know them as ELF files. I never memorized acronyms that I don't need to memorize. But yeah, Any more questions while this is running? Go ahead.
You're compiling a Rust program that's going to run on the microcontroller without.
That's the goal.
The goal is to run a Rust program that doesn't have an operating system, that runs without benefit of an operating system.
Right. So it still has an operating system, but it's not like going to be like it's much more. You're running a dedicated application. So think of it less as like a multi-application operating system and as a single application operating system. So it does one thing really well, and it runs one application and one instruction set. So you're not having to run multiple applications on it. You're simply running one specific set of instructions with all, and you've seen like the bottom of a pin for like a large CPU if you're putting it in a desktop machine where it has like gajillions of pins. Well, the Espressif chips only have them up to the side, and there's only I think like 16 on each side. I think. I mean, I can even look. Oh, 8. Yeah, there's 8 on each side. So that's 32. So you have 32 inputs, 32 outputs. And that's how it gets broke. That's where the Arduino board comes in to play, because you have all of the pinouts go to all the different parts of the inputs and outputs to that particular chip. So you have fewer inputs and outputs because you have a much simpler application running on there. And the performance of these things is compared to like a CPU is not great. I mean, you're talking about a 40 nanometer node, process node, which is for these things that like your iPhone 12 I think has like a 5 nanometer process node on there, which lower number means faster essentially. So your Espressif 32 is going to be slightly slower than the Espressif 32C3 is going to be slightly slower than the older iteration, only because it's running a new problem set at the same process node, and so there's a slight efficiency difference, but you're able to run more applications. You're able to there are more modules on there that are available to you. So there's some advantages and disadvantages to this, but there's a whole. Oh, it's finished. But yeah, I'm not sure if I explained why you would want to do this very well. If there's any questions or comments about that. Because I dove right into this, and I was like, I was super interested, and I wanted to learn about and whether or not I could put Rust onto one of these chips. And turns out that I wasn't alone. I went on a hack a day, and it was like 8 other people. So let's see here. All right. So it's going to be hard for me to do any actual coding because I can't see the screen here, but I will be able to show you the environment that we've created. So it's not very well delineated. Let me see if I can get my cursor to at least. This is the worst.
You want the lights off? Maybe that would help.
No, it wouldn't make a difference because it's just completely dark.
I get to less, get rid of the colors.
Yeah. Hang on, LS. Which pipe is that going to be less? Is it less in front or behind? There you go. So as you can see, there's ESP IDF, which is its own GitHub repository that we've downloaded. Main.zip is what breaks out into Rust ESP32 example main, and then Rust build is another repository that's on GitHub. And I can just pull up the pages real fast, the GitHub pages. So we'll get out of this virtual machine real fast and open up my browser. I'm probably just going to switch over to mirroring here in a second, if there's an AV person. I don't want to turn it off. I just want to make it not be there anymore. Oh, there we go.
Go into your display settings.
All right.
Displays.
That's not.
What happened when I did that? Try plugging that real quick. There you go. So now you're mirrored.
Okay, great. Now our screen's mirrored. We have a browser. Although it probably want to have this legible even to me. Can y'all see that? Yep. Okay, great.
Can you zoom in?
I'm working on that.
Okay.
Is there a hotkey? Yeah. Great. So here are the repositories that we were looking at. This was some of the Hackaday articles that I was looking at. So you've got your Hackaday articles. This is the Rust ESP32 example repository, which includes a number of examples. I was able to basically run a blinking hello world application on the Arduino, but or on the Arduino form factor here, but I was not able to get that running on the Mac on the MacBook through the virtual machine because I can't seem to get the virtual machine to recognize the USB input to this on this machine. So that was a last minute oh, that's not going to work. But at least I gave you the like gist of like how it works of like, and I'm hoping that I've gotten across the fact that this can be done. So I think I think I'm running out of material to go over without sort of repeating myself. Yes, go ahead. No, behind you.
Could you start some code? Like, what does the API look like? I assume
Sure.
you have syscalls and stuff, so must be something weird different, right?
Yeah. There's a couple repositories that I can show you. There was one open here somewhere, if I can see it. That's main.c, that's not Rust. There's a build. That's not right though, is it? No. I thought I had one open. Well, I'll look for that. What was the other question what was the question that you had?
What does it mean for the microcontroller to come with Wi-Fi support and stuff like that? Like, are you flashing the Wi-Fi support yourself?
Yes.
Is it a hardware module that knows how to do Wi-Fi, or like?
Oh yeah. So there are okay. Like now we're starting to get into where I might be able to explain things better. So there are actually there are actually ESP32C3 cargo Rust. Like there are actual cargo things that can access these access these modules. And there's documentation still being written. Unfortunately, I wasn't able to find anything that was that was particularly legible at this stage. But I was able to find that that these modules are the pinouts for them is starting to get broken down for Rust and particularly for the encryption modules. Like that's where my interest is. Like I want to be able to essentially take in an input. I want to be able to take an input from, say, a sensor or an antenna, and be able to take analog data, turn it into digital data, and then break it down into encrypt it, and then on the other end, of say a data transmission, be able to decrypt it, and then break it down. So
all of what you described is done in Rust.
All of that can be done in Rust, and can be done. It can be done very efficiently in Rust, and without leaving any sort of trail into the memory on it, and without being. And Rust, one of the biggest advantage to Rust is that you're not as open to having a firmware exploit where somebody's jumping in. Somebody's executing code that's going to execute something nefarious onto your system, which is the whole reason why you would want to do this in the first place. That was the whole discussion about industrial controllers and things. I just wish I had the time. I wish I had more time to really dig into some of this stuff and prepare before I dove so deeply into this. But I do know it's possible because I was actually able to run some very simple code onto this thing. I just can't seem to demonstrate it off of the MacBook. So yes.
I noticed one of the crates you're using is a Hall crate.
Yes.
Can you take a moment to explain the difference between that and a regular crate, and why would you use a Hall crate?
So they're I'm trying to think of how to explain it. Whole crate Rust. Sorry, I'm very tired.
You missed the Hall. No, you don't. No way out.
Gosh, I can't even see the screen. Oh, this is for STMs though. My answer is I don't know why the HAL crates are different for this particular set. I'm assuming that it's like specific to the manufacturer, but I don't actually know. So I haven't dug quite that deeply yet. Yes. Sorry.
Are you, when you're essentially compiling these chips, are you using the standard Rust runtime and like a standard lib, or is there essentially some different runtime for embedded devices?
you're essentially taking the one of the things that I was showing earlier with the code, with the difference in the code, is that you're actually not using stable, you're not using nightly, you're using ESP, and it brings a whole different set of libraries to link to. It brings a whole different set of things to build this environment, and it runs it on a different. Like if you're on an ARM machine or if you're on an Intel machine, you're going to be running it through an emulated environment in order to be able to compile it into RISC-V 32. Yes, I know. I saw you earlier.
I'm seeing that there's like a peripheral access crate for ESP32C3. What other like useful libraries are there that we could use to target that particular chip?
The libraries that I've been specifically looking for or looking at are all to do with. Let me pull up my slideshow again. Let's go ahead and just show it here. So I've been specifically looking at the hardware acceleration for the cryptographic things, specifically the block cipher. So I know that there exists cargo crates somewhere. I can't remember where, but they do exist for the block cipher specifically and for the SHA hardware acceleration. But the documentation is non-existent. So it's about sort of hand jamming and trying to figure out what's going on with that. I don't know about the other the other peripherals and sensors. The GPIO is going to be pretty standard. So the things that you're gonna see there are probably going to be very similar to what you see in a wiring Pi crate, like you would see with the Raspberry Pi. But obviously, there's a smaller amount of GPIO, like it's the smaller version as opposed to the full broken out one that you would get with wiring Pi. Yes. Oh, sorry. I missed you.
So Rust kind of like gives you a bunch of tools for dealing with like memory safety and
Yeah.
like concurrency stuff, but like I guess a lot of what I think of when I think of security analysis and like just these kinds of things, making that kind of software safer, is also ensuring that the software that you write like conforms to the like correct protocols. Have you like encountered any of that kind of stuff when you're looking at this kind of like the divide between ensuring that the code that you're implementing, even if it's in a memory safe language like Rust, is actually like protocol correct or like correct?
Yes.
Like
Yes.
And, like, is there like an overlap that you're familiar with between using Rust and then maybe trying to like make that tooling collaborate a bit better with, like, you know, to make sure that you are actually implementing protocols the right way?
Yes. So being able to ensure that the code that you're executing is executing properly, you know, the hard part is the fact that you're essentially trusting these cargo crates to be written in a particular way. So if you are going to be doing like the security work that I'm doing, I am having to do these deep dives into actual cargo crates and looking at code and looking for errors or poor, you know, code. A lot, you know, Control F for unsafes is a pretty good way of determining whether or not, you know, something is written well or written poorly pretty quickly. You know, because I've seen a lot of code that where people just throw in. I mean, there are cargoes out there that have, you know, up to like 60 or 70 unsafes in one you know, RS file. So, you know, you've got, it's finding things like that you would want to do if you were developing firmware for something production grade, which is what you would want to use Rust for. I'm just at for me personally, and I think most people who are doing this right now, because there is a sort of small community of a few hundred people who are in this space and playing with these things. It seems to be that it's mostly trying to get familiarity and develop these cargo crates and ensure that they're well written now, as opposed to like being ready to go for production systems, for production applications and things. So the reason why you would see like a dev board right now that just came out, like the dev board that we were looking at earlier, this thing I think has been out for 6 months. It's, and I only got it like 4 weeks ago. It showed up finally after, because it came from Australia or something. So, and it's a really good dev board. It has a lot of features that I'm really looking forward to playing with. Unfortunately, I just didn't get enough time. I didn't get enough time to play with it before doing this presentation. Yes.
Can you talk a bit more about the security module, like what it's for and how you work with it? Is it like kind of like a phone where you have like an API for interacting with the security module?
Yes.
Okay.
So one of the advantages to the security modules on these things, on the microcontrollers themselves, is that the security modules, the traces of how the hardware works are set in stone. Like they're essentially they're the equivalent of chisel. They're lithographed in to such a point where numerous years of almost 40 or 50 years of security research have ensured that these different components work fast, they work efficiently, and the inputs and the outputs are always going to be the same, and there's no muddling up of the data that's going through there. It's very fast, it's very efficient. So it is instead of having to actually run code, you're simply telling Rust, hey, go to this module, do this thing, so that way I can execute the task that I need to and get the results. So as opposed to like writing Rust code itself and going through each single step of say an RSA, prime factor factorization process. You have the separate module. You're basically throwing data towards the module and receiving the outputs and expecting that to be working out every time.
So does the security module like guarantee against like side-channel attacks, like timing attacks or something?
It makes it much more difficult, especially because of how low power the chip is, and because of how because of things like shielding and things like that you're going to have on a production system. Like you would want to take those kinds of security measures into account. But at the end of the day, it's a really low power chip. Like you're not going and I'm getting a bit outside the scope here because now we're talking a bit more about the security of it. But from like a side channel attack perspective, you're not going to be able to measure as much heat differences. You're not going to be able to measure as much RF frequency leakage. You're not going to be able to see as many like effects or impacts because of just how tiny and low power and efficient these chips are. Whereas like if you're using a large high powered CISC x86 CPU, you're much more vulnerable to those things. Also, you're going to have a lot more applications running on those things. You're going to be running a multi-application kernel. You're going to be exposing one application set of code in memory to another application set of code in memory. So really outsourcing secure security applications to a single hardware unit that you can also put as a peripheral. One of the advantages to microprocessors is their enormous flexibility. Like essentially, you can think of them as being like a peripheral device to a CPU based device, and that's what that's why you see microprocessors so regularly in peripherals. Why you see it in graphics cards or modules that, like PCI cards and whatnot for different things. So, and on ASICs, like ASICs are essentially glorified microprocessors. Yes.
So I'm a little confused as what it actually means to talk to one of these peripherals. So the code is running on the CPU.
Yep.
And then it's writing data that goes to a peripheral and then just reading the response, and that's the level API to
Yeah. I mean, you'll see that on the board breakout itself, like you're going to see like with this, on the board breakout yourself, you have all of these different inputs and outputs that go to the different traces on the chip itself. So what Rust would be doing is it would be taking inputs and outputs that, if you were to attach it as a peripheral, then it would be like a TX. It'd be like a transmission. It would be like the transmission of data between maybe two traces and that device, along with the power and whatnot. So or you can think of it as like if you're putting like an LCD hat, like one of the cute things about the Arduino form factor is that you can already get these very simple peripheral we've got I didn't even pull these out of the box yet, but like little LED lights, buzzers, potentiometers, and things you have your peripheral. Essentially your peripheral microprocessor is going to also have peripherals as well, so you can take inputs and outputs, and it's hardware, so it's you are not having as many. You're not having as many things being exposed, to the outside elements or to, from a security perspective. If you're running an industrial system, you're going to know that input and that output is going to be, that specific input and output every single time. So you have the advantages of running microprocessors and hardware and offloading onto a hardware device are going to be the fact that you have way more control. You just have way more control, and you're not going to have as many problems as you're going through this process. On the other hand, though, that's what's led to the problem from the security space, at least, with industrial controllers having so many hardware security vulnerabilities and firmware security vulnerabilities, is because these things sit there for long periods of time and they don't get updated, because you have so much control from an industrial component perspective that that whatever C code or maybe even basic code that you're running on this thing from whenever it was built is not going to be updated. Now then, the disadvantage, unfortunately, you're not going to be able to run, you're not going to be able to Rustify an old, some of the older chips. But you are going to be able to take new chips that can that have the same traces, that have the same capabilities, that have the same inputs and outputs as these older ones, and just replace that, and then run a different single application kernel on there. So you're running a very simple application, and if you really want simpler introductions to this, because this is pretty intermediate. This is a step above your Arduino, above your simple Arduino. If you want to get simpler, then I recommend that you actually look at the Free Spirit. What is it? The Free Spirit Express. I can't find it. There's specific software. So basically, there is specific software that you can use that runs much simpler code, non-Rust code, in order to like introduce you to this stuff. But you know, like this was an intermediate. Oh, here it is. The Freematics. There's a company. Freematics is Esprit C3 is ESP-C3. Okay. So the Freematics builder is just a lot simpler. Like you're going to be able to run like much more beginner level code on this thing to be able to learn about how to do these about how to run things on this. But this is a beginner level. Like you would probably want to be familiar with how to put some basic Arduino code, like your pretty basic interpreted language code onto an Arduino before you would want to flash it with Rust. But I just dove right in there, so sorry. I think I'm gonna wrap it up with one more question. All right, go ahead.
So I wanted to run Rust on Arduino.
Yes.
Not the RISC-V. It turned out to be really hard, so what I ended up doing is compiling to WASM and running to a WASM program.
Yeah.
Think about that. What actually worked great. I basically imported all the functions from the Arduino libraries.
Right.
And I have a full Rust running on Arduino. It's probably slower, but it's nice.
Yeah. So yeah, people have. It turns out somebody's doing it. So it is out there. It is in the wild. I managed to get it working, but yeah, it's hot. It's like this is. I want to just be clear. This is like bleeding edge stuff, and I'm in my own work. I'm just starting to dig into this. Like some of these chips are only starting to get delivered to people's doors. So I'm going to wrap it up here because I'm running out of material. And I'm running out of answers. But